Welcome. In this session, we will be discussing how to do certain basic analysis on dataset. We have over here the dataset serve. This is the imported form of the GSE 4922 dataset already given to you. I've already loaded the spreadsheet and named the resultant dataset as serve. What does it consist of? It consists of the patient identifiers as the first three variables, then the grade of breast cancer, the genomic grade of breast cancer, the follow-up time of each patient in years, then in months, then the recurrence status, RFS, ER status, lymph node status, P53 status. P53 minus means P53 wild type, P53 plus means P53 mutant, the age in years, and the size in millimeters. Even though this data set was originally meant to validate or see the prognostic effect of what is known as the genomic grade, we will be using this data set to examine the relationship of P53 status to the other prognostic factors. Now, before going any further, we should define what our variables actually are, what sort of a variable they are. We know over here the grade of breast cancer, that's an ordered categorical variable, grade 1, grade 2, grade 3, an increasing order of uh, aggressiveness. Then ER status, that's a categorical variable, ER negative, ER positive. That's a categorical variable which is dichotomous. Lymph node status over here has a categorical dichotomous nature, negative and positive. P53 is categorical dichotomous. P53 minus meaning P53 wild type, P53 plus means P53 mutant. Age in years is continuous, and size in millimeters is a continuous data. Now, let us first try to examine the relationship between P53 and ER status. Remember one basic thing while analyzing data statistically, you should always follow a simple basic rule: description and visualization first, followed by proper selection of test, followed by a proper inference. Now, P53 is categorical, ER is categorical. How should we visualize these two? We should visualize these two by means of a bar graph. So, first let us get into the EZR. Once we go into EZR, we select serve, we go into graphs and tables, get into bar graph. Now, bar graph, what do we see? We see the relationship between P53 status and ER status. So, first let us see, let us draw in color, let us see what it looks like. Now, while seeing this graph, P53 mutant has been shaded green over here, P53 wild type shaded pink. We can see that ER positive tumors are far greater in number, and even though the P53 mutant, the absolute number is possibly greater in the ER positive cases, the proportion of uh, P53 mutant tumors is greater in the ER negative group. We can visualize this better if we just add a graph of proportions. Just so compare proportion in each group, P53 with ER status, and here we have it. In ER negative tumor, Slightly more than half of the tumors are p53 mutant, while less than one-fifth of the ER positive tumors are p53 mutant. So, if we have to find the relationship of a tumor, what do we mean by relationship between two categorical variables? One of the easiest ways to understand the relationship between two categorical variables is to see if the proportions are different in the joint proportions are different for the categorical variables. If the proportions of the variables of the relationship that is the same amongst the variables, that means as one variable changes, other variable does not really change. There is no real relationship. If there is a difference in proportion, we can say that as one variable changes, there is a concomitant change in the other variable. They are related. Over here, we can see that as we go from ER positive to ER negative tumors, the p53 mutant status actually increases. So there is a possibility of a relationship. But to find out actually if the change in proportion or the difference in proportion is statistically significant, we should be doing a statistical test for that. What is the test we do? For two categorical variables, we do the Fisher's test. Now, alternative to the Fisher's test is the chi-square test. How do we do that? We go to the statistical analysis, click on discrete variables, click on create two-way table and compare two proportions by Fisher's exact test. Over here, row variable p53, column variable ER status. We can keep any percentages we like. We have clicked Fisher's exact test. We can, if we want, click the chi-square test also, but we are keeping that for now. We click OK. So at the end, we get the result. For the Fisher summary table, this is the cross tabulation. The cross tabulation is a nice way to describe the relationship between two categorical variables. We see that there are actually lesser number of ER negative patients, a total of around 34, of which 19, more than 50%, are p53 mutant. The number of ER positive patients are far greater, 209 over here, of which 39, which is less than 20%, is actually p53 mutant. And the difference in proportions, we can say, is statistically significant at an alpha of 0.05. It is statistically significant even at an alpha of 0.01, simply because the p-value over here, 0.00000127, that is far lesser than 0.01. Now, let us come to the details of the tests over here. We get certain other details provided by EZR. While seeing the exact test for count data, we get the same p-value of 0.000127. Now, over here, check out what they have written. The alternative hypothesis, true odds ratio is not equal to 1. That means the null hypothesis tested over here is that the odds ratio is 1. Odds ratio is 1. This null hypothesis is the same as stating that the proportions of the rows and columns or the proportions of the variables remain constant. Now, they have given a sample estimate, an odds ratio of 0.1828018. We have to realize what this odds ratio means. Odds ratio over here means that in this case, the odds of the getting ER positive result in P53 compared with the odds of getting the ER positive in P53 negative, that is P53 wild type cases, is 0.18. It is far lesser. So the probability, the odds of getting the positive cases in P53 mutant cases are far lesser than that in P53 wild type cases. How much? By how much? We can get that by odds ratio of 0.182818. Odds ratio can range from 0 to infinity. The null value, as we have already stated, is 1 if there is no relationship between the two dichotomous variables. The odds ratio will be 1. 0 to 1 means uh, when you move from one category to another, the probability of finding the other variable decreases. There's a sort of negative relationship. Odds ratio of greater than 1 means these two variables are positively related. That is, as you move from one category, say from P53 wild type to P53 mutant, you get a higher chance of getting the other variable. So that is what odds ratio means. I can also tell you one thing, it's very, very difficult to imagine numbers ranging from 0 to infinity, and these two are not exactly symmetrical. 0 to 1 and 1 to infinity, they are not exactly symmetrical. For that, if we want to describe the relationship using a somewhat more symmetric statistic, we can use what is known as the Ewell's Q. Now, remember the term Ewell's Q? That's not calculated directly in ECR, but you can calculate it quite easily numerically. Ewell's Q is just Ewell's Q is just odds ratio minus 1 divided by odds ratio plus 1. So just remember this, Ewell's Q is equal to odds ratio minus 1 divided by odds ratio plus 1. In this case, this will range from minus 1 to plus 1 with 0 in the middle. An odds ratio of 1 will correspond to a Ewell's Q of 0. Odds ratio less than 1 will correspond to a Ewell's Q less than 0. The least value that it can take is minus 1. The more close you get to minus 1, the greater the negative relationship. Ewell's Q of plus 1 corresponds to odds ratio greater than 1. Let us see what's the Ewell's Q is in this case. Over here, the odds ratio we got was around 0.18, 28018. Let us just do the calculation and find the Ewell's Q over here. Odds ratio minus 1, that is 0.1828018 minus 1 divided by odds ratio plus 1. Let us see what is the value of the Ewell's Q. The Ewell's Q is minus 0.69090004, that is minus 0.69. Quite a high absolute value, around minus 0.69. It is closer to minus 1 than it is closer to 0. We can see that the relationship is quite strong. Now, how do you assess significance of the odds ratio? You look at the 95% confidence interval. You see that the confidence interval, both the sides, both the ends of the 95% confidence interval are quite low. Even the upper confidence interval of 0.41664034 is lesser than 0.5. Usually an odds ratio of 0.5, you can just calculate it over here, corresponds to quite a high Ewell's Q. 0.5 minus 1, 0.5 plus 1. And that corresponds to a moderate effect size of minus 0.33. So, if the yield skew is at the absolute value is greater than 0.33, you can say that there is at least a moderate effect. If the yield skew does not have a absolute value as high as 0.33, maybe the effect is not that great, even though you may get statistical significance. We can see over here that both the confidence intervals corresponded to a large effect. Even the upper confidence interval, upper limit of the confidence interval was quite low. That is why we can be confident that there is a strong negative relationship between ER status and P53 mutant status, and that is also statistically significant by the Fisher's exact test. Let us see now what about the relationship between P53 and lymph node status. We can always, and we should be visualizing it by the graphs. P53 over here. Let us, instead of BR status, click on lymph node. Let us just see the proportions first. Now, this is the proportions that we see. We see that for lymph node negative tumors, which were more in this data set, okay, the proportion of P53 mutant is quite similar, to that of the lymph node positive cases. There is a slight difference, and we can check out the difference in proportion and visualize that easily by checking the proportions. Compare the proportion in each group. We see how that looks like. The ER positive tumors seem to have a slightly higher proportion of P53 mutant tumors, but the difference in proportions is really not that marked. We can visualize it directly over here by the graph themselves. So let's see if this turns out to be statistically significant. We click on discrete variables, go by the same way. P53 status instead of the ER status, we click on lymph node status. Do the very same thing, Fisher's exact test, continuity correction. That's not needed, that's only for the chi-square test. We click on OK over here. We get a p-value of 0.0514. We get the numbers, the cross tabs, but the p-value we get is of 0.0514. That is, the p-value is greater had we taken an alpha of 0.05. This is not exactly statistically significant. This shows that we cannot reject the null hypothesis that there is no difference in proportion. We cannot state that confidently. What about the odds ratio? Once we come over here, we see that the odds ratio is 1.88, not very high, it is borderline high. The 95% confidence intervals are on both sides of 1. One is the lower confidence interval is lesser than 1, it is around 0.97. The upper confidence interval is 3.65. That is why we cannot be certain, or we cannot actually say with a great deal of confidence that there is a positive relationship. However, there is another point we see from the confidence interval. This upper limit of the confidence interval is quite high, 3.65. Usually, an odds ratio of 2 is considered to have a moderate effect size. The upper confidence interval is greater than 2. So we cannot be certain, even though we this statistical test did not achieve statistical significance, we cannot be certain that the odds ratio is not actually very high. In this case, this usually is a result of inadequate sample size. We can get greater information if we repeat the experiment after getting a higher sample size. Now, we had seen that with the Fisher's exact test, we got a non-significant p-value. Now, what have we done the other valid test, the chi-square test? With the chi-square test and with the continuity correction, we click on OK, get the Fisher's p-value of 0.514, and the chi-square p-value is 0.06. So, the chi-square test also corroborates the Fisher's exact test in giving a non-significant result. So, that is that about finding out relationships between two categorical variables. We use the Fisher's exact test, but as we saw, if we actually visualize the data first, we can actually be more confident and we can actually support our data in our minds better. Let us go on and find out the relationship between P53 status and grade. Grade is an ordered categorical variable. For finding out the relationship visually, what can we use? We can use the bar graph. Let us see what the bar graphs looks like. First, we see the raw data. We visualize the raw data over here. We see grade 2 patients are the highest. But one thing we can actually visualize, even with the raw data over here, the proportion of P53 mutant cases are far lower in the grade 1 patients as compared to grade 2 and grade 3 patients. Is there any relationship in the proportions? We can visualize that better with the proportions right now. Let us look at the proportions. Let us compare the proportion by the bar graph. What we see is as we go up from grade 1 on to grade 2 on to grade 3, the proportion of P53 mutant cases increase. They increase progressively. The proportion of P53 mutant cases in grade 2 cancers is higher than that of grade 1 cancers. But for grade 3 cancers, that the proportion of P53 mutant cancers is even higher than grade 2. There's a clear-cut relationship over here of progressive increase of the P53 mutant status as the grades increase from 1 on to 2 on to 3. So what is the test we can use? Of course, we can use the Fisher's exact test or the chi-square test. We can create two-way tables. Now we can put grade over here and do both the chi-square and the Fisher's exact test. And we get a very significant p-value, a p-value 3.24 e minus 11. The e over here means 10 to the power of 3.24 into 10 to the power of minus 11. That's much lesser than 0.01 or 0.05, which are the commonly accepted alpha values. For the chi-square test, again, we get a very significant value. So we can say that there is a significant relationship. The null hypothesis of the proportions being equal in all the three grade of the P53 mutant status is rejected. One of the things we see, this was a 2 by 3 table. Since it was a 2 by 3 table, we cannot calculate the odds ratio. We have to make use of some other effect size. Usually, the effect size that we can use for over here is the Somers T or something like Kendall's tau. But explanation of these two are beyond the scope of the present session. Now, Fisher's test is valid for categorical variables, but we know that grade is actually ordered categorical. In order to increase the power, we would have been justified using another analysis. For discrete variables, you go down and there's a Cochrane Armitage test for trend in proportions. This is possibly a more appropriate test if one of the variables is ordered categorical. So over here for Cochrane Armitage test, you have a binary variable over here. P53 is binary, dichotomous, and the grouping variable is grade, and we check out whether there's a linear trend. We can see something of a linear trend. We can visualize that in the bar graph by the side. But let's see if we can actually justify the linear trend by the statistical test. We get the result of the Cochrane Armitage test for trend and proportions. The p-value again is far, far lesser than 0.01. And once we get such a significant p-value, we say that this supports our contention that there is actually something akin to a linear trend in the P53 status when the grade is progressively increasing. For the Cochrane Armitage test, the null hypothesis is there is no trend. That null hypothesis of no trend is rejected over here. The Cochrane Armitage test is an appropriate test when you are comparing a dichotomous variable with an ordered categorical variable. Let us move on to the other important prognostic factor, size. How does size relate with P53 mutant status? Again, the dictum holds. First, visualize and describe. Let us describe this first. Size is a continuous variable. We get into the summaries. Size in millimeter. We see what statistic to select. We summarize by groups over here since we are interested in the groups. P53. Okay. And we get the summaries over here. As we can see from a basic description, the mean size in the P53 wild type is 20 mm. In the P53 mutant group, it is 28 mm. So there is a difference in size. However, the variability in the P53 mutant group is higher. The median size of the P53 mutant group is also higher than that of the P53 wild type. The third quartile is higher, the maximum is higher. So, this is the description, but it would be more appropriate possibly to visualize it. We can, of course, check out the histogram for the size, but one of the basic ways to do a side-by-side analysis is by a box plot. Let us do a side-by-side box plot over here. So, we do the size. I prefer a whisker range of the first quartile minus 1.5 into quartile range. That's just me. That's also the default setting in the default R program and in many other statistical programs. The grouping variable is P53. Let us see what they look like. Over here, we see the box plot. This box plot actually supports the contention that the sizes of P53 positive tumors are actually higher than P53 negative tumors. However, these seem to be extremely skewed. Let's see what the description of size actually is. We can see how size is distributed by the histogram. Okay, and let us see it according to the P53 status. What we see over here by the histogram, two side by side histograms, is that size is extremely skewed. The distribution of size is extremely skewed. It's not symmetrical. So, if it is not symmetrical, that means we cannot be using, or it may not be appropriate to use a particular type of test known as parametric tests. Okay. Besides this, when it is such a skewed distribution, the mean is not a very good indicator of the central tendency. We should be preferring the median over the mean and preferring the interquartile range, the third quartile minus first quartile, over the standard deviation as a measure of variability. A very common thing to do while analyzing the data is to confirm what is known as the Gaussian distribution. How can we confirm whether the distribution is Gaussian? We confirm it by means of a quantile comparison plot. Let us see for the size. We want to see whether the distribution is Gaussian. The other name for Gaussian is normal. Let's see what this curve looks like, the QQ plot. The QQ plot, as we see, does not follow a straight line. If it were a normal distribution or a Gaussian distribution, all the points would have been close to a straight line. We see at this point, it begins to diverge upwards. So, the distribution is not actually Gaussian. We can also see or check whether the distribution of the size in P53 wild type and P53 mutant tumors are Gaussian or not. But for that, we have to make use of another part of the menu. We have to go to the uh, heading original menu, put graphs. Over here, there will be quantile comparison plot. Click on that. Click on size millimeter, plot by groups. In this groups, there will be P53. Put OK. Click OK at the end. And what you have over here are two quantile comparison plots. One graph, one quantile graph, one QQ graph for P53 wild type tumors, one for P53 mutant tumors. And in both these cases, we see that the points do not lie on a straight line. The assumption of Gaussian distribution is violated in both. In this case, we cannot be using what is known as the parametric test possibly. Now, how do we test for differences? If the Gaussian distribution, if the assumption of normality held, we could have gone over here. These are unpaired data. We could have gone for continuous variables and done a two sample t-test. Size for the response variable, the grouping variable was P53. We do not assume equal variances, and we could have clicked OK, got a graph of the differences, and we go to the main output window. It shows a statistically significant value, but as we saw, the Gaussian distribution, since the assumption of a Gaussian distribution was violated, possibly this is not an appropriate test. So we have to use what is known as a non-parametric test in this case. How do we get the non-parametric test? We just go for continuous variables or the non-parametric test over here. The non-parametric analog of the unpaired t-test is the Mann-Whitney U-test. We click on Mann-Whitney U-test, see size in mm, put P53 as the grouping variable, and click OK. get the bar graph as the default uh, in ECR, but when we go to the output window, we are finally we see the table, we get the summary results, the median size of P53 wild type tumors and the median size of P53 mutant tumors. We already saw that there was a difference, and the difference is statistically significant p value of 0.000000841. This is even lesser than what we got by the t test, which shows that at such a violation of the Gaussian distribution, this non-parametric test is not only more appropriate, but it is also more powerful. So we just saw how to do a two variable test. What if there were three grouping variables? For example, if we had to see the relationship of size, say with grade, what would we have done over there? We would have, of course, visualized the size with grade by means of a side by side box plot. We can see that in grade 3 tumors, the size is greater than in grade 2 tumors, which is greater than in grade 1 tumors, and it is also skewed. In this case, we would have had two options. Of course, we can see the whether the assumption of normality holds. We go to the original menu, graphs, quantile comparison plot, size but when we see plot by, we do not get the grade over here. That is because in the original plot, in the original menu, they are very strict about the variables. Grade, since it has been numbered as 1, 2, and 3, that is being treated as a numerical variable. We have to convert grade into a ordered categorical variable. Go to active dataset, variables, okay, and then convert numeric variables to factors. We get grade over here. We give a name to the variable. Let us say factor grade. So fact grade, and we use numbers for the factor levels. So okay. So we have made a new variable fact grade where the grade was converted into an ordered categorical variable. We can see what fact grade actually contains. It would be the same as the original grade. There are 68 grade 1 tumors, 126 grade 2, 55 grade 3 tumors. Now, once we go to the graphs, quantile comparison plot, size now we get the fact grade over here. We click OK. Okay, and we get three quantile comparison plots. And in all three, we see that the points are not on the straight line. The points are diverging from the straight line. The assumption of normality is violated in each and every grade. So, we should not be using a parametric test. Had the parametric test been valid, what we would have done was we would have gone to continuous variables and done a one-way ANOVA. The response variable is size. The grouping variable would have been grade. And we click on a pairwise comparison over here. Click OK. What we see is, even graphically, there's a clear-cut difference between the grade 1, grade 2, and grade 3 tumors. This is the graph which shows that this is the mean of grade 1, this is around 18 mm, with the standard deviation, the mean of grade 2, that is just above 20 mm, the mean of grade 3, that is around, it's quite close to 30 mm over there. We see that there's a clear cut difference in size, and on seeing the output, we see that the differences between the grades, uh, the results of the ANOVA is highly significant. What the results of the ANOVA mean is that the size of at least one group, okay, size in mm of at least grade 1 or grade 2 or grade 3 are higher or lower than the other groups. It does not show that all three are different from one another. In order to know whether all three are actually different from one another and how they differ, we have to do the post hoc test, which I had clicked in the menu. Over here, we get the results of the post hoc test over here. We see that the difference between 2 and 1, that is significant at a p-value of 0.02. The difference between 3 and 1 is quite significant, and the difference between 3 and 2 is also quite significant. Over here, we get the numerical value of the difference also. Between 3 and 1, there's a difference of around 11.89 millimeters. Between 2 and 1, there's a difference of around 4.65 millimeters. Between 3 and 2, there's a mean difference of around 7.23 millimeters. However, we had already seen that the one-way ANOVA would possibly not be an appropriate test because it assumes normal distributions. What we should be using in this case would, in the eyes of the purists, possibly be a non-parametric test. What is the non-parametric equivalent of the one-way ANOVA? It is the Kruskal-Wallis test. We click on the Kruskal-Wallis test. Response variable is size in this case. The group is grade. And if the result is statistically significant, we would want to do a pairwise comparison later. So we check out one pairwise comparison algorithm. I prefer the Steele-Dwas pairwise comparison for a Kruskal-Wallis test. I click on that. I click OK. First, we are greeted by the visualization of the differences, but we can go to the output window, check out the p-values. We get the Kruskal-Wallis test p-value is 6.98 E minus 10. This just means, as I've already told earlier, E represents 10 to the power of. This p-value means 6.98 into 10 to the power of minus 10, a value far, far, far lesser than 0.01 or 0.05. So it's highly significant. The null hypothesis is there is no difference in size between the three grades. That null hypothesis is violated. This just means that the size of one of the grades is different from the others. Which one is statistically significant? How do the different grades stack up one with one another are known by the post hoc test. We selected the Steele-Dwas test. Between 1 and 2, over here we get something known as a t-value and a p-value. The p-value is, check out over here, between 1 and 2, the difference is significant. Between 1 and 3, the difference is significant. Between 2 and 3, the difference is significant. Which one is greater or which one is lesser can be seen, of course, by seeing the descriptives. That can also be guessed by looking at the graph. We can see that the sizes of the grade 1 tumors are the lowest, followed by the grade 2 tumors, followed by the grade 3 tumors. So, in this session, We started with comparison between two categorical data, followed it up by a comparison of one categorical variable with one ordered categorical variable, which we followed by a two sample test for continuous variables, both Gaussian. The Gaussian one is the unpaired t-test, as well as the non-parametric. The non-parametric equivalent is the Kruskal-Wallis test. And we followed that up with the one-way ANOVA for comparing more than two groups, along with the post hoc tests and its non-parametric equivalent, which is the Kruskal-Wallis test. We also emphasized on the importance of graphic visualization. Looking at the graph itself, we can get a good idea as to whether there is a significant difference between the groups or not. And we learned how to assess normality by means of the quantile comparison plot. Thank you.